Yeah. Thank you, Sarah, for introducing me, and good morning, everyone. Thank you for joining the my presentation today, and it's my pleasure to present my work to the Wayne State University seminar, and I would like to thank Industrial Engineering Department of the Wayne State University. So today I will gonna present my part of my actually PhD work which is like dynamic data driven adaptive real-time location tracking system for workflow improvement. So yeah, so let's get started, and don't hesitate to ask any question in between. So we can I can just answer. So workflow analysis. Basically, the workflow analysis is the flow of work or material through the space. And as an industrial engineer, you know, like any of the production facilities actually have the workflow which start from the raw materials till to the production. And every stage, there are some value addition actually happens. So, and measuring this and understanding this workflow actually gives a competitive advantage to the management because they can efficiently and effectively manage the entire process within the which improve the productivity. So usually in traditional workflow, workflow actually study, people use the direct observation methods. So like someone sitting there and just see how much time like every worker is actually spending on, or how much time each process actually take. However, if there is a manual labor involved, so with direct observation or with the video based analysis, there will be some privacy issue, and also it will be high cost if we someone is taking note of the times and all that. And also if you do the interview and self-administered report, sometimes it happens on the healthcare industry. So that actually uh, that actually imputes some bias into the data collection phase. So therefore, I have actually proposed a real-time location tracking system to enhance and enable the autonomous workflow analysis. So at the beginning, I will just I will want to share like what is actually RTLTS. So RTLTS is not actually new technology. So it's basically a real-time location tracking system at indoor or outdoor. And in our day-to-day life, we use GPS for real-time location tracking system. However, GPS doesn't actually perform well in terms of the location tracking inside. And when we need more granular information at like centimeter level, so GPS is not actually a good choice for that purpose as well. So there are several technologies other than GPS people use for the location tracking system at indoors, such as the radio frequency identification, ultrasonic or ultra wideband, and also the Wi-Fi. So, and also there are actually a lot of application nowadays when there are actually industry 4.0 revolution is going on, also the lot of IoT applications we see in the industry. So their activity monitoring, then robot routing, supply chain management, those actually use the uh, this real-time location tracking. And also by tracking, there are actually two meanings. Like when we just track the like just the location of the continuous location of the object, and you can just track each time when it enters into the process. Here we are particularly talking about the first one, where we continuously monitor the location of the object. So for the RTLTS, so basically, as I mentioned, there are multiple technologies. However, based on our application, so I have researched on that different technologies and found out that like RFID and UWB are actually more suitable for our case. First of all, the RFID has actually no maintenance, especially for the passive RFID, and it can provide reliable indoor localization, given that the algorithm is actually good, and also like since the RFID signal actually is different from the signal that we use on the mobile devices, so therefore it actually there are less signal distortion, and also you can have like large cover area and it can be easily scalable. On the other hand, the UWB is also scalable. However, the device cost is high and it has actually the power inside. So you have to recharge the devices every time. And it's true for both Wi-Fi and BLE. However, for the same, those devices are almost the same cost. However, the UWB actually provides better indoor localization accuracy compared to the Wi-Fi or Bluetooth-based technology. Okay, so which is why I have chosen RFID and UWB. So this is actually overall framework. I will, in my presentation, I will go through the different modules, but so here you see like that we have RFID system and UWB system, which are the hardware part of our location tracking system, and getting the signal information and the location information from those systems that actually used for RFID based localization and the tracking, and also for the workflow analysis purpose. So what actually the RFID system? So basically RFID system consists of 4 components. So first, it has the reader and the antenna, and also the PC for processing the signal data. And we also definitely there will be some RFID tags. So basically the PC actually sends the reader the program that needs to be executed, and reader broadcasts the signal based on that program and via the antenna. So when the antenna actually transmits the signal, basically it creates an electromagnetic field which charge the UHF, or which is called ultra high frequency RFID. So charge that RFID tags, and those tags um, the modulate the signal and then send it back to the respond back to the antenna, which is then read by the reader and processed by the PC. So that's how it actually works. So since the passive RFID doesn't have the uh, uh, power source, so that means it should be within the like the line interrogation zone, which is called the field that created by the antenna. So if it's not within that, it will not be detected by the RFID system. On the other hand, the UWB system, basically that one has like the anchors, which is here, and the tags, and it's wireless. So it actually sends communicate with the computer with some device called listener. So I will go much into detail in the later portion of the presentation. So, and then we have the RFID localization and tracking unit and workflow analysis unit. Okay. So here you see that the RFID localization and tracking unit, it's basically coming from here. Like we have this this unit, which is actually the consists of 2 separate units. One is the modeling unit and the tracking unit. So all the hardware that I have explained for the RFID, that actually sends the received signal strength information and also the tag ID and the antenna ID along with the timestamp. So we need to actually develop an algorithm that can use that received signal strength and then transform it to the location. So which is why I have actually developed a regression model that relates the received signal strength with the distance. And then I have generated a fingerprint database. So basically the fingerprint database refers to a grid of points uh, for which the received signal strength is estimated via the regression model. So, and then this database, so for instance, like we have one location XYZ, and for that one, we have a fingerprint database, have the information regarding the received signal strength. Let's say we have three antennas. So there will be three received signal strength information for that particular location, and it applies for the other fingerprint location as well. And later, actually, those data will be compared with the actual signal coming from any of the RFID tags in the real time, and we'll compare that and use the tracking unit to track the actual object. And how that actually is actually happening here, you see like there are some location ranking estimation, which because in this case I'm actually using the k-nearest neighborhood algorithm, so therefore I need the location ranking, and then also the transition matrix and emission matrix is actually generated from the data collected at the experiment phase, and using those it will create an hidden Markup model, and later it will be decoded by the wider research algorithm to decode the path. So let's jump into more detail, so how that actually works. So why actually a hidden Markup model? So basically the hidden Markup model, it first of all, it actually fits the assumption that for the tracking needs, it actually continuously we have continuously timestamp received signal strength information, and we actually it has in our case the next moving location depends only on the present location, and it's not actually totally independent or not related to the past states. So therefore, the HMM is a good choice for this case. And also, like it's there actually you see here like we can determine the likelihood of the sequence of observation and in the process of the HMM, and predict the next observation in the sequence of observation, and need to find out the most likely underlying explanation of that. So let me show like how that the HMM framework actually looks like. So here you see this is the basic structure of the HMM that applied for the tracking algorithm. So we have the location information for each of the state. And then for each of the states, so from the starting point, so the object can move to the any of the state, and the latent information that we have is basically the received signal strength information vector. So using this one, we can actually track the ranking of the location, and later for each of the location we can find for each case. So when we get the new signal, basically that one actually gives the another state, and it actually goes on. So after if we can collect all those information, we can solve this using the vital research algorithm in the later step to decode the path. And also here to determine the ranking, I have used the sum of square errors from the actual by comparing the fingerprint database along with the actual signal. So that is one. And also for the emission probabilities, I have actually used the inverse of the distance calculated by the regression model to calculate the probabilities for the of the transition probability, and also the for emission, it's the inverse of the sum of the square errors. So that's how this hidden Markov model is actually formed. And later it actually solved by the wider research algorithm to find the optimal sequence of the movement. So you remember, like for each stage, we have multiple locations. So we need to find out what is the next location in the chain, and with the maximum likelihood. So basically, so it's initialize the step at the starting point, and having the starting point, we need to find out what is the most likely next position, and so on. So this is one of the typical example of how the like the location tracking looks like. So let me give some of the other experiments and results that I have found after applying this algorithm. So we have performed actually multiple experiments. So at different speeds of the object, in this case, the human beings, we are targeting to track. So, and we have studied multiple patterns. So you may wonder like why the zigzag and the zigzag vertical and horizontal, because both are actually look same with the different orientation. However, like it is important in terms of the RFID, because it depends how the RFID antenna is located. So in our case, there were actually 3 antennas, so which is arranged on a like in a on the vertices of a triangle shape area, and and then it actually used to collect the information. So therefore, we need to have the orientation as well. So, and then also for the some of the data regarding the RFID is like the sampling period is like around 0.5 seconds, and basically the algorithm runs every 10 seconds. So basically we're gonna make 20 predictions in each cycle to have the tracking. And we place the tag on top of the tiger and the human. And for human, it was 3 tags, so that we don't actually lose any line of sight of the tags. So you see, like this is one of the experimental setup. So these are 3 antennas, and those are the fingerprint location for which the data is collected. And then I performed actually with this small toy, and these are actually line tracking toys. So I put the tag on top of that and use that information uh, to develop this actually algorithm. And so that's how it's actually the data collection actually happened at the experiment phase. And after collecting those actually the data, so we need to apply it actually to the real actually case, and that and also need to validate it. So basically here you see we have like it's an example of 3 by 3 grid, and where you see like there are actually all these are the fingerprint points. So, and we have information regarding that. So let's say we have one of the tag that is moving from L1 to L2. So, and based on our algorithm, we actually look for the locations that are calculated by the k-nearest neighborhood algorithm. So this is the outcome of the k-nearest neighborhood algorithm ranking. So here you see one, two, actually 15 different points are ranked because we have 15 fingerprints. So, and then we found like what is the possible location. So a person cannot move within the certain speed. It cannot go beyond actually 1.5 meters. So that's how it's actually limited. And then we found the best ranked actually coordinate for any of the location for as a next location. So yeah, and then if you like, let me give you an example here. So here you see like we have a line tracking toy moving around the rectangular path and the circular path. And this is how our actually tracking algorithm track the position at different time step. So, and these are actually at results at different speed. So here, one thing, the accuracy that I have actually achieved for this one, it's around 0.36 meter. So the average error, considering sometimes the maximum error actually go beyond like 0.8 meters sometimes for the RFID. But comparing this technology, the passive technology, this is actually a good accuracy for the indoor tracking. So unless we need actually more accurate information, accurate localization, in that case, we have to actually choose different technology for the RTLTS. So, so for the application of this RTLTS, I have been actually I have actually worked with the grafting process for the implementation of the RTLTS. So as I mentioned earlier, like the RFID, so we got accuracy around average accuracy of 0.36 meter. However, in this case, I have to track like the human movements. So, and we need actually more than that. So, which is why for this analysis in the workflow of the grafting, I have actually uh, used the UWP, which provides the better accuracy. So let's give a overview of the grafting first. So basically, this is a horticultural technique that combines the compatible actually the upper part of the plant and the lower part of the plant to like two different plants to have actually better yield, because the lower part have better pest resistance and environmentally more strong. And on the other hand, the upper part is actually high yielding part. So which actually provides more vegetable or the fruits compared to the plant based on the lower part. So those two are combined. So as you see in the picture, so, and the process actually combined of four steps, like the sign cutting, which is the upper part, then rootstock cutting, then clipping, and we next phase is actually joining. So it is very critical to study this workflow at the each step, because these are perishable items. And for this kind of perishable item in the process, so if there is any bottleneck or if there any time delay for processing any of the plants, it will eventually impact the yield of the plant in the long term. So, and therefore, this is very important for the analysis for the grafting in this grafting, and also the grafting works are very labor intensive, and therefore it's managing the workflow for the productivity and also the success of the grafting is very important. Okay. And so as I mentioned earlier, that the RFID accuracy was not good enough, so which is why I have to use the ultra wideband, which provides the better accuracy. And and it actually provides accuracy with location accuracy with in less than 10 centimeters, so which is good for our application. And also the UWB actually works at pretty high frequency, so it can overcome many obstacles in and and it can actually track the object behind the obstacle, so within a certain range. So here you see actually the typical structure uh, of the UWP framework. So basically it contains actually four components. So the anchors, tags, listener, and the gateway. So anchors are similar to the antenna in the RFID, and tags are just similar to the tags. The only difference is here all of the tags have the power source for itself. And then we have listener to collect the information. So basically the listener uh, make bridge between the tags and between anchor and tags to the computer. So it collects all the location information provided by the UWP and send it to the computer. And if we have actually we need larger actually network, or we want to cover a large area with multiple rooms, separated rooms. So in that case, gateways need to be used. So gateway is basically the combination of the Raspberry Pi and also the UWP tags, which gives the UWP the uh, option to get connect to the internet, and we can have the location information via the server that provided by the vendor. Okay. So here you see like the study actually happened in one of the grafting facility, which consists of multiple departments. So have healing, germination, then grafting, shipping, office, and restaurant. So basically, I will gonna focus mostly on this area. So in this here, the plant are actually grown, and after the plant are grown enough, and then it goes to the grafting section. And here that four process cutting, science and root stocks, clipping, and joining actually happen, and then it goes back to the healing department. So, and for this work, you see the arrangement of the tables, and here in the location A, the sign cutting and rootstock cutting was happening, and B, the clipping, and on the C, the joining was happening. So I have deployed the UWP system throughout this facility. And here you see this is the origin that is defined and based on which the anchor locations are determined. So these are the red triangles are the anchors. And there are tags, and there are actually a lot of tags there, and it's actually tracked by these actually anchors, and the data is collected. So now the question is, how we actually gonna find out what based on this location system, and we don't see anything. How can we determine the time for each process, or how much, and also how they're actually going through from each one step to the another step. That's to do that, I have actually proposed a workflow analysis framework. So basically, this is the UWP system we have, and we have multiple modules to process the data, and we've got a movement, detect the movement, and analyze the workflow. So for the movement detection, I have used the change point detection for the time that you mostly used for the time series data, because we are getting continuous stream of location information. So, and based on the origin, we can estimate, we can calculate the distance. So if there is a change, sudden change on the distance, we can say that like the object is moved from one location to the another location. And after that, there are some actually techniques I applied to remove the overlap between the time period duration of the worker and the trace. So later I will explain that as well. And eventually it will show the final result in terms of the Gantt chart, which is easier for the which is actually a lot easier for the management or the whoever actually conducting the process to understand what is how the process is performed, what are the waiting times, and how can we actually allocate different resources to avoid any kind of bottlenecks within the process. And those are actually fully automated process. So once it's deployed, so it can actually pre-process the data and give output of the Gantt chart. So a little bit overview of the data. So we usually get the data like this with the timestamp, tag information, and XYZ coordinates. And those information are then pre-processed to get the like first it actually due to the limitation of the resource, I used like the tag twice for a single tag for two different trays. So I need to separate that. So let's ignore this one. However, and then for each of those tags, hello? Your car is finished, but there wasn't any room. So for each tag, actually, this location information are then processed, and we need to find out what is the change point looks like. So here you see the application of the change point. So basically, this is the distance it's showing, and whenever it moves from one location to the another location, it actually collect that change, and then that one is actually pre-processed by the algorithm. Okay. After detecting the change point, we can identify like what is the duration looks like for each of the location. However, there are actually two types of overlap happen during this process. So one is the worker overlap, and other is the tray overlap. So it happens basically in the RTL when the tags are locations informations are collected, the tags actually doesn't know whether it's with the tray or the worker. So for the worker, if the same tag actually assigned if the algorithm identified the same tag for two different workers, but it's not possible for this process to have the same tray processed by two different workers at the same time. So therefore, we need to remove those. So here you see tray 1 and tray 2 processed by worker 1 and worker 2. So here you see there is an overlap. So this one is resolved by comparing the distance from the worker tag and the tray tags. So which one is closer, that is actually assigned to for the tray. So here you see after resolving the overlap, how the flow actually looks like. And on the other hand, a single the tray overlap actually algorithm. So it I think this one is the same picture. So basically the tray overlap algorithm overlap actually happen when there is a single tray processed by worker overlap actually happen when single tray processed by multiple trays processed by the same worker, and tray overlap happens when multiple trays processed by the same tray processed by the multiple workers. So that one is removed by comparing the distance between the tray and the worker. So that is one important step for the workflow analysis. And after analyzing all this data, so it comes down to different workflow matrices such as the processing time, flow time, and what are the different wait times, and that will be shown using the points using the Gantt charts and other bar chart for the visualization purpose. So here you see like these are the tag location information, and this is really looks messy. And after we apply the algorithm and we simplified the visualization, as you see here, the process actually moves from one location to the another location. And for each of the location, we can estimate the duration or the time spent by each of the tag. So, and it's associated with the tray. So we know which process it's actually going through and how much time it took for that process. So this is one of the Gantt chart for the tray, how it looks like. So we have 16 trays. And then here you see for each of the tray, how it actually we had actually 4 workers for the one for the sound cutting and rootstock cutting, to another for the clipping, and the last one other 2 worker for actually the grafting purpose, the 3 worker 3 and 4. So here you see how it actually moves from one process to the another process. And also if you check the mostly it follows the sequence worker 1, 2, and 3, or worker 1, 2, and 4. But sometimes the worker 3 actually is the expert in grafting. So he actually showed up for the he took the job for that cutting and cutting the rootstock and science as well. So, but it provides the how the each process actually flows and how much time they actually spend. And this is another one that for the worker. So basically it shows for each of the worker when they actually process the different trays and how much time actually they spent. So this actually gives the all idea about so you see there's a lot of in between processing waiting times. So basically that will create the bottleneck eventually. So we need, the purpose of this one is to find out those kind of improvement opportunities using the RTLTS information for the workflow. Okay. So if we go deeper into the data analysis, so here I have actually plotted into the bar chart for the 3 different matrices, like the processing time, flow time, and the in-process wait time. So we have detected like for 3 of the trays, the flow time is really high, and due to the in-process time was unusually longer. It was because like, so we have actually work in process inventory. So one tray processed by cutting, and then it goes to the clipping station. So let's say there are multiple trays comes into the clipping station, and then the worker actually forgot which one comes first or which one next. So, and then he or she actually left that tray for a long time. And later when got time, that one is processed. So that is time when this in process wait time actually happens, and it waits there. However, it's actually detrimental for this kind of time sensitive process. So that is why it's we are interested to find out like how that actually happened and how can we like remove that. And next one you see here, so for the some of the exceptional cases like where tray is processed by 2 workers instead of 3, because like the one worker is faster than the other, so he took over some other uh, other processing work instead of, let's say, someone is assigned to grafting and he's done with the grafting. On the other hand, the person who was doing the cutting and clipping, they are not done. So at that time, the grafter actually helped them. So that's how sometimes we didn't get the exact flow of the work, but we identified that using the RTLTS information. Okay. And then I have actually performed the outlier detection to find out which trays have taken unusually long time for different process. And also, as I mentioned earlier, we had actually 4 workers. So those workers, this is how their processing time distribution actually looks like. And just for your information, that worker 1 and 2 are considered as novice, and worker 3 is the expert one. So even from the RTLTS information, it turns out that he was assigned for grafting, but even the grafting is the toughest process among the all 4 process. He spent actually less time for each tray compared to the cutting and clipping. So which gives actually idea about the worker efficiency as well, and how they're actually how proficient they are in the grafting task. And for the workforce, he's a part-time worker, so he didn't actually process much of the trade. So there are actually a lot of variation with the small amount of data, because there are only 4 data for him. And I have also collected, so one of the method I mentioned at the beginning, it's the direct observation. So basically I have collected the data using the direct observation method as well, and compared the outcome of the RTLTS with the direct observation. And it turns out that the time duration detected by the algorithm is around 90% accurate, most of the cases in detecting the time length of each of the process. So therefore, I can say that we can safely use that RTLTS technology for the workflow analysis. And since we can apply it for the indefinite amount of time, so it can actually provide a real-time tracking as well. And whoever actually manage the process, they can see and act based on what is the real time, what is actually going on in the facility, or in other words. I have shown the example for the vegetable grafting. However, this application is not limited to vegetable grafting. This is actually applicable for other manufacturing process like the job shops or the flow shops. So where we can actually see how much time they spend on each station. So, and in conclusion, actually, I have showed the real-time location tracking for the RFID, and how and also the UWP technology applied for workflow analysis. Some of the future works that I am planning to do if I get time. So like the combination of both RFID and UWP RTLTS system, and then extend it for some other facility, other actually applications. So I think that's all I have. So if you have any questions, so I'd be happy to answer.